So welcome everybody to our fifth seminar in the Algebra, Particles, and Quantum Theory seminar series. I'm pleased to introduce to you tonight's speaker, Shahn Majid. Shahn is a professor in the School of Mathematical Sciences at Queen Mary University of London. Shahn completed his PhD at Harvard under the supervision of Arthur Jaffe and Clifford Taubes. He later went on to win a long string of fellowships at the University of Cambridge before eventually starting with Queen Mary in 1999. Shahn's main research interests include non-commutative geometry, quantum groups, algebra, category theory, and quantum gravity. He's written 4 books, namely Foundations of Quantum Group Theory, a Quantum Groups Primer, On Space and Time, and Quantum Riemannian Geometry with E.J. Beggs. In 1993, he won the Bleuler Medal for his research on quantum spacetime, quantum differential geometry, and quantum groups. Shahn is best known for his early contributions and influence in the field of quantum groups. He initiated a quantum groups approach to non-commutative geometry and the use of these methods as a route to quantum gravity. So tonight, Shahn will be telling us about his quasi-associative construction of the Octonions. Now, before we begin, I'd like to emphasize that everybody that showed up today is here to learn. And so I hope that everyone feels comfortable enough to raise their hand and ask a question through the talk if you have one. If you accidentally ask a silly question, it's not a big deal. You just brush yourself off and try again next time. I would especially like to encourage questions from graduate students, upper level undergraduates, and postdocs. Okay, so please go ahead, Shahn.
Thanks very much, Cohl, for that very thorough introduction. So firstly, I just want to mention, I looked through the participants. I see some old friends, people there. If those of you who already expert on Octonions won't learn anything new, but you're welcome to ask questions and interrogate me anyway. And I want to echo what Cohl said, that everyone should feel free just to interrupt me. If I don't see you raise your hand on the Zoom thing, just turn on your microphone and shout. Okay, now I promised just some possible points of contact with physics, so I think I'll just get them out of the way right away, and then the rest of the talk will really be a maths talk, maybe a little bit at the end. So for me, the sort of main interest has always been quantum gravity. We don't know what that is, but it's got to go to classical GR in some limit. So you might think that quantum gravity effects could be modeled by non-commutative Riemannian geometry. It's just a hypothesis. There's no proof for it. I call it the quantum spacetime hypothesis. And so that suggests inventing a whole kind of geometry that works when coordinate algebras are non-commutative. Now, that's a far cry from particle physics, but bear with me for a second. Now, there are some known, using this approach, there's a kind of big formalism that has been developed that's in this yellow book with Beggs. And there are lots of models constructed. And because quantum geometry works on any algebra, it even works on a finite dimensional algebra. For example, functions on a set of a few points. So a finite just functions on a set of 3 points. It's just a 3-dimensional commutative algebra. But the geometry still works and you get non-trivial results. So these are the first models of finite quantum gravity. You can pursue everything to the end, assuming you accept the quantum spacetime hypothesis, and you don't mind your model being very small, but it fits all the axioms. So I consider that a finite quantum geometry, and then you can just compute everything for quantum gravity, and it's all finite and works. I'm not saying that's going to win any prizes because the universe doesn't consist of 3 points, but I think it's a good start. Now, this relates to particle physics, potentially, if you take Alain Connes' idea, and his idea was to tensor product the functions on ordinary Minkowski space by a kind of extra dimensions. And when you extra dimensions, that means the algebra gets a tensor product. And here we tensor product it with a finite dimensional algebra. So it's exactly the kind of finite geometry I was just describing. And then what Alain does is he has a different conception of non-commutative geometry, which I won't go into. Maybe at the end I'll say a bit more. But anyway, he has a notion of non-commutative geometry of finite dimensional on a finite dimensional algebra. And then when you analyze, take the picture of the whole space-time, it's a kind of Kaluza-Klein idea, but with the extra dimensions being non-commutative, because the algebra A is going to be non-commutative. then in Kahn's work, he finds that how it appears from the point of view of fields on the Minkowski space is as multiplets of fields, and he can choose A in such a way as to recover the standard model. It's a bit cooked up, and physicists haven't really been convinced by it, but it's a nice idea, even if the implementation is still lacking. Okay, now today's talk is going to be about the Octonions. And my view of them is actually exactly as a geometry. I think of them as quasi-associative and quasi-commutative. So actually, I would say, I'd go so far as to say, Octonions are actually commutative and actually associative. And you'll say, well, that's crazy, they're not. But they are, if you look at them the right way, that is to say, in the correct category. And so that result is in this paper with Albuquerque. And what I will talk about specifically, if you want to know more about it, the most modern treatment is an exercise in this yellow book. So you'll see a few more details. Now, so one idea is to stick these Octonions, the algebraic, into Kahn's idea, and then see what kind of multiplets you get. And then that isn't too far from the kinds of things that are being proposed by Cohl and by Jeffrey Dixon and by Rob Wilson. I mean, I'm not saying it's the same, but it's kind of in the same spirit. Now, another possible contact of physics with physics, and you can also just think of Octonions by themselves as a finite geometry and do quantum gravity on them. That's a whole other story. Now, the third point of contact with physics is more conventional. The constructed Octonions I will describe are actually based on a group and a cocycle. And if I give you a finite group with a 3 cocycle, you can build a category from it. That's what will happen with the Octonions. But that category also is of interest, depending on the group, is also of interest in TQFTs. So there were papers by Witten and going back to the 80s about TQFT, so like the quantum group constructions, but using a quasi-Hopf algebra rather than a Hopf algebra. And the sort of underlying thing is the double of it. So Digraph, Pasquier, and Roche worked out the double of a finite group with a cocycle. And so there's some literature on TQFTs with this quantum group symmetry. And so the Octonions are in that family. The Octonions themselves aren't that interesting from that point of view, but they are technically in that family, and one could do things related to quantum computing and TQFTs using the Octonions if you really wanted to. I think it would be relatively interesting. I mean, so in this context, the TQFTs in the context of a discrete group, but without the non-associative element. For example, if you have Z2 cross Z2, these are cool, so without any kind of non-associativity, but they are of interest in quantum computing. They are they're called the torus code models. And so this would be a non-associative version of that, yet to be investigated, but also relates to physics of TQFTs. Okay, so those are some possible contacts of physics. I may try to come back to it if I have time at the end. Now, firstly, this construction is going to take place in a braided category. So what is that? I'm not going to be overly mathematical, and I promise to be very concrete by the end of the talk. So a collection of objects, let's call them VWZ, and a tensor product map. So I've given 2 objects, I can take their tensor product. And then what are called functorial isomorphisms. It just means that they actually relate the 2 different tensor products, this one and the opposite one. But what that means in practice is if I've got any 2 objects, V tensor W, there's an isomorphism with W tensor V. That's the opposite order. Similarly here, this natural transformation relates this double tensor product with this double tensor product, with the brackets ordered like that. And possibly I got them the wrong way, but anyway, something like that. And I think it's okay. And that means, in practice, what it means is that for every 3 objects, V, W, and Z, there's an isomorphism between V tensor W tensor Z and V tensor W tensor Z. So, and the fact that everything is functorial, it just says that these isomorphisms, they commute with any maps between objects, so they just behave nicely. Okay, now an example that you're already familiar with, which is a bit trivial, but still interesting, is the supervector spaces. So the objects are the category of Z2 graded spaces. That means that every object splits into 2 pieces. One is the 0 component and one is the 1 component. Z2 is 0 and 1. And morphisms, that means maps between them, are linear maps that preserve the grading. And the associator is just a trivial one. So there is no it just associates them without doing anything. Changes the brackets. But the braiding has a sign -1 to the degree of the thing. So this is what you're familiar with in supergeometry, or in if you work with differential forms, you've got a similar kind of Z2 grading. Now, what Maclane's theorem says that actually you don't have to worry about the associator because it just takes care of itself. There are certain rules that phi has to obey. I haven't told you what the axioms are, so I'm not being too overly mathematical, but there are certain axioms. In particular, phi obeys a pentagon identity. And when that holds, I'll show you that on the next slide, but when that holds, then you can basically forget about brackets. That's what Maclane's theorem says. What he says is you can write all your constructions if there are no brackets, and then whenever you need in brackets, just insert phi so that things make sense. For example, if you were grouping W and Z here and then doing whatever you want with it, or if you're alternatively grouping them the other way and doing whatever you want with it, then for those constructions to be compatible, you would need to compare them. You would need to map over using phi to change the bracketing. So you would just insert phi at that point whenever you needed to for things to make sense. And all the different ways that you could insert phi would give you the same answer. That's Maclane's theorem. So you don't have to worry about it. Okay, so monoidal category is not something to be afraid of. Here are the axioms. So for the pentagon, for the associator. So you take the fourfold tensor product from one order of brackets to the opposite order of brackets. And there are two ways to rebracket to get there. So for example, this way, you're just rebracketing, leaving U alone, you're rebracketing within here, between the V, W, and Z. And I see the conventions are the opposite of what I just said, but never mind. Then I'm rebracketing again, considering WZ as one object. So V, WZ as one object, and U, rebracketing it the other way. And then I'm rebracketing it again to get to this one, leaving V alone, and rebracketing WZ and U. And so you could also go the other way up here. And those two ways to do it, to be the same, that's Maclane's pentagon identity. And what he's saying is once you take care of that, then everything else is taken care of. Now, given Maclane's theorem, we're going to have a diagrammatic notation where we don't even write the tensor products. So for example, VW just means V tensor W. And VWZ means V tensor W tensor Z. And I don't care about the bracket because of Maclane's theorem. And then from that point of view, I'm going to write the braiding going down the page as a braid crossing. So this is swapping V and W. And that's the morphism that I mentioned at the beginning, this tensor product between the tensor product and the opposite tensor product. Natural transformation. And the inverse I'm going to write as an inverse braid crossing because I don't assume that the square is the identity. If the square of psi is the identity, like it is for superspaces, then we say that it's actually a symmetric category, not strictly braided. Now, the W's obey hexagon identity. I mean, the psi's obey hexagon identities. If I wrote them like this, they would be hexagons involving some phi's and some psi's. But if I've omitted the phi's, they look rather simpler. They just say that if you group VW as one object and you braid that past the Z, treating it as one object, it's the same as first braiding W past Z and then braiding V past Z. Okay, it's kind of obvious, right? So that's the obvious consistency condition. Similarly, on this side, if you treat W and Z as one object and braid it past the V, it should be the same as first braiding V past the W and then V past the Z. So that's here's V past the W and then V past the Z. Okay, so and punctoriality I mentioned was just that if you've got any other map or more allowed map between objects, then you can just pull it through braid crossings. So the Joyal Street coherence theorem says that these diagrams really capture all the information. If you've got two diagrams that look the same topologically, up to what's called isotopy, then if you write out the corresponding maps, they will compose to the same composition. You may have to connect them via appropriate phi's. So that's the coherence theorem for braided categories. So this is as much math as I'm going to tell you today. It's just really reassuring to know that everything works in a coherent framework without things without having to worry that things are going to get too complicated. Now, we're going to be focusing entirely on a particular type of example, which is the category of G-graded spaces. So so G is going to be a finite group. An object is going to be just decomposed into pieces, and those pieces are going to be labeled by the group elements. So instead of 0 and 1, it's now labeled by the group element. And so the degree, if we say that V has a degree mod V, and it has that value G, if V lies in VG. So all the components for a fixed G, they have degree G. And I'm writing the degree with a modulus sign. And now the data I will need is a 3 cocycle. And this is an ordinary, if you look in a book on group theory, this is an ordinary group 3 cocycle. It'll be valued, in that case it's valued in R, but it depends on three group elements. And basically what it says is if you multiply the first 2 and then apply it, or you multiply the outer 2 and then apply it, it's the same as multiplying the middle 2, or taking the first 3 or the last 3. And this actually is exactly the same as this diagram on the preceding page. It's exactly this. You see, when I applied the associator here, leaving u unchanged, I was just using phi in the 3 positions, in the first 3 positions. Then in this case, when I applied phi using the middle 2 as one object, I was really looking at the value here multiplied, and the value here, and that is just this leg here. Okay, so I guess I needed to explain that a bit more. There were 3 objects here. One was the first one. Then I did this one here, which was grouping those together as one object. Last one I did, I left V alone. I just took the last 3. So now if you look at this, it's the same thing here. I did the first 3 elements, leaving L out of it. Then the middle 2 grouped together as one, and then the last 3 elements leaving F out of it. So that is one side of Maclane's pentagon, and this is the other side of Maclane's pentagon. It just happens to be a 3 cocycle. So what that tells you is that this category of V-graded spaces is actually a monoidal category, and this is the associator. The reassociation of V, W, and Z, bearing in mind I got my brackets around in opposite conventions, but let's just use these conventions from now on. So I don't. So V. The only thing that's wrong is this diagram. I should have been bracketed in the opposite order, but don't worry about that. We'll use these conventions. The associator is that it's just the trivial associator doing nothing but multiplying it by this phase, by this factor phi, which is this group cocycle, according to the gradings of the vectors which are involved. Okay. Now, in group theory, an important question is a cocycle the coboundary of a cochain? And so that says, is phi the coboundary of F? Well, what that means in practice is phi of F, G, and H given by this combination of a single function in 2 variables F. So F is the 2 cochain, so it's a function of 2 variables. And if it is, then you can show, this is what I observed in my paper with Helena, is that actually this becomes a symmetric monoidal category, and here is the braiding. So actually we take F and divide it by its flip. So if F was symmetric, this would be trivial, and then you get this. So this ratio gives you R, and this function R plays a similar role to phi. It determines the braiding. So just when you braid 2 things one past the other, it's a usual flip, but with an extra factor. So for superspaces, this is plus or minus 1. So superspace is already an example. In fact, let's see that very soon. Now, before I go back to concrete examples, let's just do a little bit more abstract thing. Using this diagrammatic notation that I mentioned, what is an algebra in a braided category? So it just means I give you an object in the category, for example, a superspace or a G-graded space. And I just got a map that says an object A, and I've got a map from A tensor A to A, reading down the page. And if I apply it twice, it's the same thing as applying it the other way around, bearing in mind that to equate these 2 things, you would actually have to rebracket. So there's a hidden rebracketing in there. The unity axiom, identity element, which I regard as a map from the trivial object in the category, like the to one-dimensional vector space, into the element A. We have to be given that map, and then it should obey this property. And it's commutative if, obviously, if the product is the same thing as applying the braiding and then applying the product. Now, what's an example in our G-graded spaces? So in our category of G-graded spaces, I can take the group algebra of G itself. So the group algebra of G, it just means the elements of G with their product, the product of G, extended linearly. That can be a bit confusing for if you're not familiar with that kind of thinking. So we can just do it very explicitly. We take a basis of A labeled by the group elements. And then the ordinary group algebra is just the product of EA with EB is just E of AB, where AB is the product in the group. So that just says I'm just taking the group product, extending it linearly. But the twisted group ring is to introduce this F. And so I'm going to stick here F of AB, the same F which was making the category symmetric. So this applies in the case where phi is a coboundary. Then I've got this F, and then this gives you an associative algebra in the category G spaces with phi given by the coboundary of F. So phi is given by that specific formula that I showed you built from F. And if you bear that in mind, it's not too surprising. You actually check it for yourself on the back of an envelope, that this algebra, that this works, and you get something which is associative in the category. So what does that mean? It means if I multiply these two first and then multiply, well, literally that means that I start with the tensor product, I apply the product, and then the result of that, I apply the product again. So that's reading from the left here. On the other hand, if I want to compare it with the other side, I've got to connect the two by the associator. So I use the associator to turn that bracketing into the opposite bracketing where these two are together. And then I apply the product here and then the product here. And so what that means is when I apply this bracket, the phi to this, I will get the other order, the other bracketing in the other position, but I'll have the factor phi of A, B, C. And then I'll multiply them, I'll apply this and this. That means I get this. So therefore it says that this product is phi times this product. So that's exactly capturing non-associativity. And similarly with commutativity, if I apply the product directly, that's here, but it's also equal to applying the braiding and then applying the product. So apply the braiding, which gives you this factor times E B tensor EA, and then apply the product. So I'll get that. And of course, that is only commutative. This first was true for any group. This is only true that I'm going to get an equality here if the group is abelian. So, but that will be our case. Okay, so we've got a construction for a non-associative, what I call quasi-associative, and sometimes commutative, what you could call quasi-commutative algebras in our category. Okay, so let's look at some examples. I'm going to show you a family of examples. Anyone who works with Octonions loves to see these three things together. Okay, even mathematicians who don't work on Octonions are fascinated by this. So these are complex numbers, Hamiltonians, and Octonions. Now, we're going to start with the complex numbers. So you take the group G to be Z2, and you just take F to be -1. So elements of the group are just X and Y. That's 0 or 1, and I just multiply them in the field, and then take -1 to that. So what's a basis? Well, a basis, this group has two elements. One is E0, which is 1, and the other is E1, which I'll call I. And let's just see what I told you the product. The product of E0 with E0 is F of 0, 0. So go over here, that's 0 up here, -1 to the 0 is 1, that's E0. That behaves like what you expect. E0, E1 is -1 to the 0, F0, 1. You put 0 here, 1 here, you get 0. So again, you get 1. Similarly here. Here you get F of 1, you get -1 to the 1 times 1. So that's -1 to the 1, so you get a minus sign. So you can see here that this works. This is I, so I squared is -1, as expected. Now here, this particular F is rather trivial. R is 1. and phi is 1. So it is actually strictly associative and strictly commutative, as you would expect for the complex numbers. Now, I just mentioned there is something else going on here, which is there's another relation in this algebra, which is visible here when you have E0, E0, E1. It's all coming from F, but it's captured by a property of F, which we can call this function n. So E squared of x is n of x, where n of x is -1 if x is not 0 and +1 if it is 0. I mention that because this property generalizes when we go further on. So as an example of a braided category, an algebraic category, it's pretty uninteresting because it's just associative and commutative in the category of Z2 graded spaces with I has degree 1, but that doesn't make it super because this is a different this is not the super category of super vector spaces because the braiding here is the trivial one, not the one for super vector spaces. So it's just everything trivial here. Okay, next one, G is going to be Z2 cross Z2. So instead of, I'm going to now think of, yeah. So F is going to be given like this. It's a function of these of an element of G and an element of two elements of G. I'm going to regard them as vectors with entries in Z2. I'm actually going to think of them as in the field F2, the field of two elements. So I'm really thinking of, but it doesn't matter, it's 0 or 1. So they're vectors with values 0 or 1. And then I'm going to take -1 to this vector, this matrix dot this vector. And when you work out phi, it's again trivial, but when you work out R, it comes out to be -1 times the determinant. Then again, it's the back of an envelope calculation. And what that means is that it's -1 because that's the determinant. That means that what I'll get is something which is 0 if they're linearly dependent. So I'll get +1, and I'll get something which is 1 if they're, because it's in the field F2 is either 0 or 1. I'll get 1 up here if they're linearly independent, which means I'll get -1 for the factor. So R is this factor which is in the same family as the function n. If you think about it, a single element x is linearly dependent if x is not 0. So that's what we had for the function n. Now we've got the same phenomenon for the function r. It's just given by this property. Phi is still trivial, so we're going to get an algebra which is, so we follow the construction, and actually what you get is the quaternions. So here, I'm going to use a shorthand. The vector corresponding to 1 is just 0, 0. I'm not going to write the brackets. I'm just going to write 0, 0. The 0, 0 is the vector in Z2 cross Z2 with values in. It's a 2 vector with values in the field of 2 elements, and that's how I'm going to be labeling things. And then I is going to be 0, 1, J is going to be 1, 0, and K is going to be 1, 1. And let's just do a little example. So for example, IJ is going to be well, it's 0, 1 times E 1, 0. And therefore it's -1 to the, and I got to stick 1, 0, 0, 1 here, and 1, 0 here. Okay. So you have to do a little calculation yourself, and you'll get 0 for the top. And so you'll get -1, so you'll just get J, you'll just get, what have I written here? That was meant to be E11, not EKK. You'll get E11, which is K. When you add these together, you'll have to add the vectors in Z2 cross Z2, because that's the group. So that 0, 1 plus 1, 0 is 1, 1. This is the typo, it's meant to be 1, 1. Okay, similarly, if I do I squared, I've got 0, 1, 0, 1. When I stick 0, 1, 0, 1 in here, I'll get a 1 here. So I'll get -1 times E0, 0, because when I add these together, 0, 1 plus 0, 1 is 0, 2, but 0, 2 is 0, 0 in the group, working in the field of 2 elements, or working in the group Z2 cross Z2. So that all works. So these are the relations except for the quaternions. Now I claim the quaternions are actually commutative in this category. And let's just check. For example, Ji times Ij, it should be commutative with the factor r, but the factor r is -1 if they're linearly independent. So is 0, 1 linearly independent from 1, 0? Yes, it is. They're different. They're orthogonal directions in R2, or in Z2 squared. So they're linearly independent. Therefore, I get a minus sign. So basically, in practice, this just means that all the distinct octonions, if we only got two, okay, in practice, it just means that if you only got two vectors, then they're linearly independent if they're the same. Dependent if they're the same, and if they're and not if they're not the same. So really, it just means that the octonions all anti-commute like this, which is what you expect. Okay, so this is what I've summarized. The category here is trivial associative. The braiding, there's a braiding which is -1 if the degrees are linearly independent, regarding the degrees as vectors in 2 dimensions, but with values in 0, 1. Okay, and these are the gradings of IJK. Okay, so with that in mind, I think you're all ready for the octonions. So we take the group now Z2 cross Z2 cross Z2. So this is now, they're just 3 vectors. I mean, they're vectors in like R3, but it's not R3, they have values 0 and 1. But they're like Euclidean vectors in R3, but just with those values. Now the matrix, the F I take is this, and it's quite interesting where this F comes from. It's a bit of a mystery, but I think of it as a kind of Chern-Simons action. You can think of this as like a finite derivative. I mean, if you were to symmetrize it, it would look a bit more like a finite derivative on a lattice. And then this is some kind of cubic term. So I think of this some kind of Chern-Simons action, but that's just heuristic. It is given by this. You just take this formula, and what you discover, this is what we found in my paper with Hena, is its coboundary. I mean, you can take anything you want for a cochain, but if you take this particular F, then its coboundary turns out to be this quantity which of interest, which is -1 to whether the determinant of these 3 vectors regarded as a 3 by 3 matrix. So that is a decent calculation. And what it means is that phi is -1 if and only if the 3 vectors are linearly independent viewed as elements of 3 vectors in the field F, working in the field F2. And so it's a little bit unusual, but it's very geometric. I just want to say the structure of this. There's a certain matrix here which has the same form as the preceding one, which has the same form as the preceding one up here. There's a 1 by 1 matrix in there. So that bit is very regular. But this bit here is a bit weird. There are 3 components. Each of X, Y, and Z have 3 components: X1, X2, X3, Y1, Y2, Y3. And here I take them all, always the 1, 2, and 3 component, but I take 2 Ys and an X, or I take X in the middle, or I take X in the 3rd place. So there's a certain symmetry to this. And an interesting property while I'm here is that if you take the Z2 Fourier transform, take this function on Z2 cross Z2 cross Z2, take this function F. Well, it's actually in this group squared. So it's a 6-dimensional. Take the 6-dimensional Fourier transform on this group cross this group, and you get the same function F, but rotated. So all the entries of X, Y, X, and Y, the vectors have to be rotated. X1 goes to X2, X2 goes to X3, and X3 goes to X1. It's only for Y. So that's a very curious property of this F. Yeah, no one's really figured out anything more about this since the original paper, but it's quite remarkable that this all works. Now, the ratio of the 2 Fs, so F of XY divided by F of YX, also works out to be interesting. It works out to be this function again. It's the function of 2 variables and 2 vector variables, and it's -1 if they're linearly dependent. But now they're not 2 by 2; they're 3 by they're vectors in they're 3 vectors. 3 hyphen vectors, and so it's -1 if they're linearly dependent, and +1 if they're linearly dependent. And if you're interested, R is also the coboundary of N. So just as phi is the coboundary of F. Now, so what you get this time is this you take the group ring, twist it by F, and you will get the octonions. So what this is saying is, and I'll show you that in a bit more detail in the next slide. So what this is saying is that the octonions are a commutative and associative algebra in the category of Z2 cross Z2 cross Z2 graded spaces, where the braiding, the associator in the category is given by -1 if the degrees are linearly independent and +1 otherwise. And it's also commutative. Whoa, I'm going ahead there. And it's commutative with +1, so they strictly commute if the degrees are linearly dependent of the elements that you're trying to swap, and -1 if they're not. So this rule replaces everything you were struggling with about where to put the signs with Octonions. It just says, just look at them as vectors and just see if they're linearly independent, and then you'll know whether there's a minus sign or not. So this is the universal rule. It actually works for all of the algebras, for C, H, and O. The rule is that C, H, and O are all associative and commutative, with up to plus or minus signs, and they all square to plus or minus 1. So these three facts hold, and in every single case, the rule is that there's a +1 if the elements involved are linearly independent as vectors, and -1 are linearly dependent, and -1 if they're linearly independent. And that's the rule. So that is a universal rule that describes all these three algebras. I think that's quite neat. Okay, let's just see how this works for the Octonions. So, of course, the key thing is to number them in the correct way. But it turns out, as far as I can tell, that the Wikipedia labeling, which is probably somewhat standard, actually is a direct binary translation. So you take the labeling in this Octonion Fano plane, and you write the numbers in binary, and those are your corresponding vectors. So this is the vector which is 1, 1, 1 in Z2 cross Z2 cross Z2 as a vector. So and we just this is just binary if you know your binary. So for example, ij with k, does it associate or not? Well, you look at the three vectors involved. The vector for okay, so I'm indicating what the numbers are here. So I corresponds to the vector 0, 0, 1. J corresponds to the vector 0, 1, 0, K to the vector 0, 1, 1. It's the same as I've embedded the Octonions in the quaternions into it. L, the extra element with the Octonions, corresponds to the vector 1, 0, 0, and then you've got these. So it's all very logical. And so the three vectors involved here are 0, 0, 1, 0, 1, 0, and 0, 1, 1. And linear combination of the other two, so there's no sign, and that's also to be expected because it's part of the Octonions. Now, the part of the quaternions. But if you take ij and l, well, you've got 0, 0, 1, 0, 1, 0, and 1, 0, 0. So these are three different axes. So that means they're clearly independent, and so you get a minus sign. So this is how you work with it. Okay. Okay, so this is what it means in practice. Now, the question, which if you're a mathematician, I mean, this is a bit off topic for physics, but since we got this far, maybe some physicists will have an idea. What happens if you put Z2 cross Z2 cross Z2 cross Z2? Okay, see here we're in a strange situation that we know all the ingredients, we just don't know what to do with them. So we know that it's going to involve these three functions, because they're the natural thing that's in the same hierarchy that we had before. The function, which is, they're now 4 vectors. So this is like the space-time version, if you like, but with values in 0, 1. And they're going to be -1 if they're independent, etc. The associator is going to be -1 if they're independent, and there's going to be this new object involving 4 of them. This is not the capital psi for the braiding. This is a lowercase psi, which is going to be -1 if they're linearly independent for the 4 vectors are independent. So now that's obviously given by a determinant. Now that one actually is a coboundary. It's for all whenever you've got even number, it's going to be a coboundary, and it's a coboundary of phi. So psi is actually d psi, and that means in turn that psi can't be d of anything. Phi can't be d of anything, because if phi was d of something, then psi would be trivial, which it isn't. So we can't write down the twisted group ring of this because we don't have an f. There is no f which will do the job. but nevertheless, from a mathematician's point of view, the thing we want to build has these structure constants, which are, we know that the length of the objects are going to be given by, the square of them is going to be given by plus or minus 1. So it's going to be similar to Octonions. We know that they're going to be commutative and associative in some sense, and it's going to be controlled by this. And there's going to be this. So, but we don't know what this role is. Now, if you want to try to make sense of it, the categorical object is not too hard to figure out. There is going to be a weak monoidal category in which you go back to the associator from the pentagon identity, and you don't require that the two ways to go around here are equal. You require that they're equal up to an isomorphism, and that isomorphism is lowercase psi. So you can make sense of that. It's a weak monoidal category where pentagon identity holds up to an isomorphism, and that isomorphism is this guy here. And it's all going to have a braiding. So we use this data. We already know how it's going to work. We know all that. We just don't know what the algebraic object is to put in it. Okay, so I'll leave that for you to think about. It's a tantalizing thing. I had a chat with John Baez once about 15 years ago, and we decided that it might be some kind of two-Lie algebra, but no one's ever figured it out. Okay, so let's go back to tiny bit. How much time have I? Yeah, I need to go a little bit faster. So, well, I don't want to go too fast. It doesn't matter. We'll just cover as much as we cover. So the last topic is going to be doing something with it. So what can you do from this point of view of the Octonions? You can do a lot of things. And if you tell me what you want to do, I can advise you how to do it. But for example, you can do linear algebra in that category of Z2 cubed graded spaces. I can do various constructions, categorical constructions, which may be relevant to whatever you want to do. But I'm going to do a little bit of geometry. So the point of view, as I mentioned, is not going to do geometry. We have functions on a manifold. Usually, you have differential forms. So you've got df. You can write it into partial derivatives on the basis dxi, local coordinates. The differential forms graded commute with each other, and obey a graded Leibniz rule. So here they graded commute and they graded Leibniz rule. Now what we do in non-commutative geometry is we keep the basic structure, but we drop the commutativity of any kind. So A could be possibly non-commutative. It plays the role of functions on the manifold. Omega 1 is going to be some abstractly defined space. We don't have to build it in a very concrete way with geometry. We just define it but the key property is it should be able to multiply from the left and the right by functions, like here. So that's a bimodule. So you're able to multiply from the left and the right consistently, associatively. And there should be a derivative, d. Now, in the non-associative version, this will become replaced by, there'll be an associator. It'll be plus or minus 1 for the Octonions. We should have omega 1 to be spanned by differentials like this. And then you can worry about the higher differential forms later by taking tensor products. So don't worry about the higher differential forms. Okay, if you want to do Riemannian geometry, it's pretty easy. You just define a metric as a 0-2 tensor. So that's an element of one forms tensor one forms. The tensor product over A is scary for physicists, but actually just says that when you think of G mu as a tensor, it's at one point X. There isn't, not at 2 points. It's not at X and Y. It's not bilocal. It only lives at 1 point, and that corresponds to the fact that we take the tensor product of the indices, the mu index and the nu index, but we take it over the algebra so that we identify the two copies of the algebra. So that corresponds to the physicist notation like this. And we should have an inverse, which just says that we have a map going the other way in a product that undoes the metric. You could define a connection. I won't have time to go into this too much, so I'm just saying it fairly quickly. But a connection, we do it like this, as a map from omega 1 into omega 1 tensor omega 1. Now you might say, well, that's not a connection, but if you have a vector field, that would be something which evaluates on a one form. So then every vector field would evaluate this, and now we get the covariant derivative along the vector field. So if you take all the covariant derivatives along all possible vector fields, I can encode that in the single map nabla. And that obeys a Leibniz rule like this, and a reversed Leibniz rule for the other side, which involves this map sigma. Now, involves some kind of braiding. You need this in order to bring df to the left to be consistent with the other terms. This is called a bimodule connection. And when you have a bimodule connection, it extends the tensor products. So connection on omega 1 also gives you connection on omega 1 tensor omega 1. And it's defined that by acting on one copy of omega 1, and acting on the other copy, and using the sigma to bring it to the right position to be consistent with the other term. And so that means you know what you mean by nabla G is 0. G is an element of omega 1 tensor omega 1. So now I define what is nabla G. So nabla G, so a Levitin-Vita connection is nabla G is 0. And also the torsion should be 0, where the torsion, again, has a very simple meaning. It's just the two ways to go from omega 1 to omega 2, either directly or by applying nabla, directly by D, the differential, or by applying nabla and then applying the wedge product. So that's the meaning of torsion from an algebraic point of view. There's also a thing called the curvature, which is given by this formula. So I'm not going to go into all this now. I just, especially as I'm not doing quantum gravity today, but if you are interested in quantum gravity, you want the Ricci tensor, so you need to have some kind of way to lift the omega 2 and then take a trace. If you can do that, then you can define the Ricci scalar, and then you can just do quantum gravity by minimizing Ricci tensor. So that, in a nutshell, is the non-commutative geometric approach to quantum gravity. I mean, to gravity and then quantum gravity. Now, I'll just be doing I won't be doing very much of that. I'll just do the beginning of that. So we're going to do it for the Octonions. So this is actually, as I mentioned, it's actually it's a twisted group algebra. So what that means is actually the group algebra of Z2 cross Z2. So from Z cross Z2. So from a geometer, that's the same thing by Fourier transform as functions on Z2 cross Z2 cross Z2. So that's the same thing as a discrete torus. So it's like a torus where you model the circle by just 2 points, Z2. So you can take the standard geometry of a torus, and you can so you can think of it geometrically like a torus, but twisted by this F. Now the twisting is what gives you the cocycle. We've seen that today in today's talk, but it also twists the differential calculus. You take the standard differential calculus on Z2 cross Z2 cross Z2, which is not. It's obviously a problem if you don't do non-linear geometry, but it's a discrete space. Discrete spaces have perfectly good differential structures. Because it's a group, it has a very canonical differential calculus. So we know what is the differential calculus for a discrete torus, and we just twist it. And what you'll get is this. You have a basis of one forms, omega 1, omega 2, omega 3. This is exercise 9.9 in the yellow book, if anyone's interested. So what it looks like is these differentials. These are Octonian elements, and D is the exterior derivatives. These are one forms. They form a basis, and these basis elements all have degree 0, so they're all bosonic. And what that means is that when you look at the Grassmann algebra, the algebra that they generate for the whole exterior algebra, they just behave like ordinary ones. So they just behave in the Grassmann manner. The associator doesn't come in. So we take the Grassmann algebra on the omega 1s, but in terms of the ij's and k's, it looks like this. So for example, these are squared to 0, like this, and you can work out the others. They're not all completely trivial. Now what about a metric? Well, a metric you could take to be, it's just an example of a metric. So I just take some one forms, take di tends to di plus dj tends to dj plus dl tends to dl. So those are my 3 independent Octonion elements, generators, if you like. And they correspond to 0, 0, 0, 1, 0, 0, 1, 0, and 1, 0, 0 as group in terms of their gradings. And then so you can take that as a connection if you want, as a metric, and then you can take the connection for it. Now a connection is not unique. It turns out you've got a choice for each of the 3 basis sort of generating elements, ij and k, ij and l. You can take either this I di tends to di for your connection, or you can take 0. So this is kind of a flat metric. So the obvious choice is to take 0. And there's an associated map, sigma, I mentioned, which does the thing. But 0 has the unusual thing that the sigma map that was needed to change for the Leibniz rule actually is -1. So it's a bit weird. This one, on the other hand, is also a bit weird. But this is just the answer. So these are the Levitin-Vita connections. I guess there's 8 of them because you've got a choice for each of the I, J, and L. And that's just an example. Nobody's really looked at. You could write down, a whole moduli. You could take any Octonion valued parameter in front, you could take omega I tends to omega j, gij, where gij are arbitrary matrix coefficients, where the gij live in the octonions. And then you could just then you could write that down as a metric, and you could just solve for the Levi-Civita connection. The associator doesn't come into it too much, because if you work with the omega i's, because they are associative, they have degree 0. But if you have, and as soon as you have non-trivial weights, if you have gij with non-trivial Octonion values, then you will start getting non-associativity. But the non-associativity will just be inherited from the values. It won't come from the differential forms. So the bottom line is, non-linear geometry of the Octonions is non-associative, but only very mildly. The only non-associativity comes from the Octonions themselves as coordinates. The differentials and all the kind of geometry remains associative, and very easy to work with. Okay, now these are. I've got one more slide, but essentially I wanted to finish at 5.2. But if I've got a few minutes, I might show you one more slide epilogue. Now, these are some references if you want to learn more about it. These are the math references, the original math work. Here. Then I've got, if you're interested in sort of Cohn's non-linear geometry, you can do that for Octonions too, cyclic cocycles. That's in this paper. If you're interested in gauge theory, so these are more physics, and that remark about the Fourier transform, that's in this paper. So this is gauge theory where we on the space of the Octonions, through using the differentials. That's a whole different question from gauge theory with the Lie algebra related to Octonions, and that's actually addressed in this paper. So if you happen to know a little bit of sort of this wider topic, the Octonions are related to the geometry of the 7th sphere. So in fact, the unit sphere inside the Octonions is the 7th sphere, and as a result of that, the tangent space of the 7th sphere is not a Lie algebra; it's a Malchev algebra. It's not, and it lives in a non-associative category. What is that non-associative category? Well, it's the one we talked about. So actually, you can view the Lie algebra of the Octonions of the 7th sphere as associative in an appropriate setting. That's discussed in this paper here. And so then you could do gauge theory with values in the Lie algebra of S7. So that's kind of the opposite one I discussed before. The thing about twisting. It has a long history, actually, going back to my a paper I wrote with Robert Urkel a long time ago. But this idea that you can twist the geometry, that sort of has survived the test of time. And the non-associative setting is described here for the Riemannian structure and metrics, etc. And then if you're interested in quantum gravity, which has nothing to do with the topic of this talk, but that's why it's in purple, but you're interested in finite quantum gravity, the first models, well, one of the early models I can refer you to is this paper here. We do quantum gravity on Zn, so on a polygon, as well as other things. Okay, so that's the formal end of my talk. I can either stop here, or I could just tell you a little bit about cons. Maybe I will just stop here, and if anyone asks me about that, I'll come back to that. So thanks very much.
Thank you very much, Shahn, for such a great talk. Does anybody here have any questions? I might ask one right away, actually. So this Z2 cross Z2 cross Z2 cross Z2 example that you gave after the Octonions, I assume that you've checked that whether or not they correspond to the Sedenions.
Oh yeah, it's not. It's not. Firstly, it has. It's no, it's not that. I've tried that.
There's a really obvious way to see it?
Yeah, I mean the problem is any kind of algebra doesn't do the job. It's not. Well, let me just put it this way. It was a long time ago that I looked at this, and I didn't see any obvious connection. That doesn't mean it is completely excluded. Okay. But the problem. I mean, you can write down that if you use a Cayley-Dickson process, then the natural 16-onion object, which is not the Sedonions, but there's another object. You can write it down, and it would be in this kind of family with the Fs, but it wouldn't involve these psis. These psis are rather special, so. You just don't see anything like this, but I guess to be honest, I can't prove that it's not the Sedonions, but I didn't see anything that resembled it when I looked like some years ago. Okay,
fair enough. So Tejinder has a question. Let me unmute you here.
Yeah.
Go ahead, Tejinder.
Hi, thanks for a very nice talk. I had a general question. So as you know, the two-dimensional 2x2 octonionic matrices can be mapped to a 10-dimensional Minkowski spacetime. The SL2O is homomorphic to SO19. Somehow that brings to mind string theory. And so is there a possibility that through your quantum Riemannian geometries, you could sort of unify gravity and the internal symmetries?
Well, you know, I like to say anything's possible, but if I want to give you a proper answer, let's just review what you said. So you take the 2x2 octonion, so that's M2 with values in O, and that I believe one can make sense of using this categorical picture. I mean, you can control it fairly nicely. And now this this maps into, is it S? What is it? It's
SO19, yeah.
SO19. But in what way is it a map? Remind me how that works. I mean,
maybe Cohl might know better. I mean, I just know of it as a homomorphism because, you know, the diagonal terms you can write as a t minus x, t plus x, and the off diagonal terms is octonion O, and it's sort of conjugate O star. We take the determinant of this, that is the metric on 10 Minkowski. That's very easy to see, yeah. Right.
But it's not the metric, it's the symmetry group, right? It's mapping, M2O is mapping into the symmetry group.
Yes.
In dimensional space-time.
Yes.
So from the point of view of physical application, you'd be thinking of the Octonions as some kind of spectrum generating algebra for the symmetry of your extended of your 10-dimensional space-time. Right? The same way like you might model SO3 using harmonic oscillator or something like that, spectrum generating algebra. So I mean, firstly, I think it's a good idea. M2O is not a hot algebra, not a group or an enveloping algebra, but it does have qualities that are not that far from it, from the composition, from the M2 structure, from the 2x2 matrix structure, means you can compose them. So you've got a kind of, it's a bit, has a flavor of an enveloping algebra. So I think that you could probably write down some kind of gauge theory with M2O as the gauge group. That's the bottom line, in place of SO19. Whether that would, I mean, that would be different, but it would give you something that would be a little bit different from SO19 and perhaps fit better with the things you want. Now, as for a grand unified theory, unifying it with other places, well, yes, once you're starting to think of the Octonions as a symmetry group in this way, you can start doing the things you would do and make model building, including the Octonions. But the only thing I would warn you is that, you know, if you need to have, to do gauge theory, you need to have enough structure, like you want to have a Lie algebra values, like SO13 to do gauge theory, to actually implement your idea. You obviously would have the algebra SO19. You would need to have the corresponding notions on if you're going to do with Octonions. So you can play around with it, but you would need to, and this is where the categorical picture could be helpful to sort out what's going on. So definitely it's interesting, I say fascinating, but I think maybe the categorical picture could help to do things in a more systematic manner.
Sure, thank you very much.
Okay, so a question from Alex. I'm going to unmute you here. Go ahead, Alex.
Alex, your microphone's muted. Can you?
Oh, yeah. It usually, for some reason, it takes two tries. For some reason, I'm never sure why that is. We'll try again. There it is. Okay.
Is it possible to see recorded video on internet later? Because this lecture is very important, and sometimes I need to view them a few more times.
I think it has been recorded. I think Cohl asked me beforehand, so it has been.
Exactly. We are recording, yes.
Yeah, but I try to find a recording on internet. I cannot.
It'll happen at the end of the Zoom. At the end of the session, it will be. It won't get saved until the end of the session, I believe.
Yeah, I haven't been posting any of the talks yet, so there's been a delay, but I'll get around to posting them online at some point.
Okay, thank you very much.
Yeah. Okay. Okay, so Sharyar, so I need to ask to unmute you. So I think you need to give me permission.
Yeah. Sorry, you're talking to me?
No, to Sharyar.
Okay.
Yes.
Okay, there you are.
Thank you for unmuting, and thank you so much for your talk. So I wanted to ask, is there an easy way to see how one would take the semi-classical limit of quantum geometry and how it would give the classical geometry that we're used to?
Yeah, that is a very nice question. There's a paper by myself and Beggs. Actually, there's a section in chapter 9.5, section 9.5 of this book, which gives you introduction to that very question. And so yes, it's actually a very interesting question. So obviously at the classical level, at the semi-classical level, the analog of the non-commutative algebra is a Poisson bracket, right? That's what gets quantized to the algebra of coordinates. Yes. That we all know. And so the first question is, what is the analog of the differential forms? And so that's here, what controls the bimodule structure when at the semi-classical level, and that turns out to be or if you like, what controls the commutation relations between differentials and functions. I think that's perhaps this becomes quantized. This is no longer commutative; it can be non-commutative. So what controls that? That turns out to be a connection of some kind. It's called a contravariant connection. It's basically a Poisson-compatible connection. So the additional data to a Poisson bracket is a connection of a certain kind. And a flat connection corresponds to an associative geometry, to associative differentials, but if you're a physicist and you've got a connection, you probably would want to have a curved connection because it's very natural to have flat things. So then you're immediately led into non-associative geometry. So from the point of view of deformation theory, I think non-associative geometry is actually very natural, but relatively unexplored, and that's the semi-classical data. Okay.
Thank you so much, Dara. But there's no parameter like h bar that you have to take.
Yeah, well, there is a parameter. Yes, you would have a parameter that controls the non-commutativity, but we wouldn't call it h bar. You'd probably want, if you believe in this picture, then the parameter that controls the non-commutativity would be the Planck scale. So, for example, the most famous example of quantum space-time, most well-studied, I should say, is the model I introduced with Ruegg, where the commutator of x with t is lambda x. So space doesn't commute with time, but the commutation relation has a lambda in it, and that lambda is the Planck scale, Planck time, and that would, if you believe, that's just by dimensional argument. If you believe that it's a quantum gravity effect, then the space-time hypothesis says that non-commutativity is because you're modeling quantum gravity effects, and therefore that's what we would expect.
Great, thank you. Okay, that's very clear. Thank you.
Okay, so next up is Torsten.
Okay. Yeah, my question is connected with the monoidal braided category, which you introduced later. Usually these categories are used in knot theory and braiding because of the obvious relation. And also part of the Richetikian-Turaev invariance. Yeah. My question is now, is there a direct relation also of these Octonion cases as a space-time to such knot structures and such things?
That's a great question. As far as I know, no, because so basically that's what I was referring to down here. So the general construction definitely is related. So you take any finite group with a cocycle phi, you plug that into the construction of, actually it's basically, you regard that as a quasi-Hopf algebra. And then if you remember how the Tura-Vera theory works, what you take is the double of that. That corresponds to Tura-Vera invariance. You take the double of that, and then I showed in a paper in LMP ages ago that what you get is exactly this quasi-Hopf algebra of Dijkgraaf, Pasquier, and Roche. So there is this. So that construction works. But if you stick in the case of the Octonions, to take Z2 cross Z2 cross Z2 and the particular phi that is there, I believe it comes out a bit trivial. So it's not that interesting. It doesn't give you interesting knot invariance. It has the potential to, but you just need, the group should be, you probably want the group to be non-abelian to get something really interesting. Okay, but the construction works, and this whole thing we discussed with the Octonions, you could write down, you could do the same thing for S3, for the permutation group of 3 elements, and then you could look for non-associative Octonion-like structures built on S3 with the cocycle, and then you could plug that into here, and you get more interesting TQFTs. So, okay, so in spirit, your question is right, but in practice, I think it doesn't give anything interesting for the Octonions.
Oh, okay. Second question. is a usual approach. Also, there's another approach to also particle physics and using Jordan algebras. I mean, this approach where the TITS building and such things. Is there also, or did you think that there's also some categorical background or for this construction which is comparable? Because yeah, okay.
Yeah, I know what you mean. I've wondered about that over the years, and I never quite figured that out. But you know, the people who like the TITS construction, they you know, they also have this hierarchy, and they see a lot of similar things. So I've never been able to see it exactly, but I would think that it's possible, optimistically. So I think it's an interesting question. You'd have to sort of, this particular hierarchy is also related to S1, S3, and S7, all right, for the spheres.
Yes.
And you know, and so there's a lot of very interesting, and so that aspect I already can see. I mentioned that the paper with Klim that already has this kind of, you begin to see how S7 enters from the non-associative, the Octonions. That's really in this paper,
okay,
with Jennifer Klim. And so that aspect, which relates to the geometrical side, we think we do understand. But where the Jordan algebras exactly come in, I'm not quite sure. So I think it's a very good question. I'm sure there's a good answer to it.
Thanks for the nice talk, of course. Thanks a lot.
You're welcome.
Okay, does anybody else have any more questions? In that case, it might be a good place to close things off. So thank you so much to Shahn for such a wonderful talk. And thank you to everybody for showing up and for your enthusiasm and your questions. Our next speaker is Peter White from Columbia University on the 14th of February. That's Valentine's Day. Peter will be telling us about something he calls Euclidean twistor unification. So thanks again to everybody for showing up, and thanks again to Shahn for explaining your work to us. And we hope to see everybody again in 2 weeks.
Okay, thank you. Bye-bye.
Bye now.